Thank you very much for the invitation and introduction. So yes, I'm going to talk about the Grunwald problem for solvable groups. I think the story starts more or less with the inverse Galois problem. So I guess all of you have probably heard about it, but yeah, let me recall. It's the classical question of whether all finite groups G are Galois over Q, in the sense that there exists a finite field extension of Q such that G is its Galois group. The answer, as it's stated here, is expected to be yes, but so far it's unknown, and it's very widely open in the general case. Let me also make a disclaimer for the talk. Basically everything I will talk about will be over Q, but it can easily be extended over number fields, and when this is not over any number field, and when this is not the case, I will say explicitly otherwise. In particular, you can also ask the inverse Galois problem over bigger number fields, but it turns out that it's actually a more restrictive question than the classical inverse Galois problem. So this is a positive answer to this would imply a positive answer to all number fields. Okay, so let me start by listing a few of the existing approaches in the literature to tackle the inverse Galois problem in specific cases. So the first, maybe historically, was due to Noether, following work of Hilbert, and it's based on the following proposition. If you have a subgroup of GLNQ, and then you take the quotient, AN over G, and you assume that this is rational. In other words, that if you take the field of G invariants of QT1Tn, this is purely transcendental, then G is Galois over Q. And the proof is just an application of the Hilbert irreducibility theorem. Because basically you just write the extension QT1Tn as an extension, as a purely transcendental extension of QY1 Yn, quotiented by some polynomial f. And then you apply the Hilbert irreducibility theorem to this polynomial f. And this gives you a way to specialize the extension, because essentially this quotient realizes what is a generic extension of Galois group G, and then you can specialize it by this Hilbert irreducibility theorem, and then you get an extension of Q with group G. So okay. Noether even conjectured that this quotient would be rational for all such embeddings, but it turned out that this was false. The first counterexample, I think it's due to Swan, but then over C, this was even disproven over C, where the first counterexample is due to Saltman. And in particular, so you have, for instance, the following counterexamples here. You have for Z modulo 8Z, the quotient is not rational, and then you have some nilpotent groups for which you can show that the quotient is not rational even over the complex numbers. And so, yes, so this approach essentially failed, like in the general setting. You can still prove the rationality of this quotient in some specific cases. For instance, if G is generated by reflections, or less recently, like if G is well, that's still from 50 years ago, essentially. If G is A5, then yes, this quotient is still rational. Okay, another approach that has been used for the inverse Galois problem is the rigidity method, that roughly starts with the idea of trying to first realize the group G geometrically as a cover of P1, ramified cover of P1, and then again using the Hilbert irreducibility theorem to specialize this cover. So it starts with a simple topological idea that for every group G, you always have every finite group G is the quotient of of a free group. And the free group is also the fundamental group of an open Zariski subset of a projective line. So yes, you can always find such a G as the Galois group of a topological cover, and you may always then descend it over the algebraic closure of the rational numbers. And the problem is actually descending it over Q, and this is not sorry, this is supposed to be a bold. Yes, but this does not happen in general. You need some kind of rigidity condition. And in this case, then you can actually define, you can descend it over Q, and you can define a Q cover, and then use the Hilbert irreducibility theorem to specialize and obtain G as a Galois group over Q. So this works in some cases. For instance, yeah, the examples that you see here, so all sporadic simple groups, except possibly M23 still open, and then a lot of the groups PSL2FP. There are really a lot of examples, but what I wanted to emphasize is that mostly it's suited for simple groups, whereas for like solvable groups, or especially like this rigidity method had some problems with like extensions usually of groups. So yes, this connects me to another approach that is the cohomological one, that instead is somewhat at the opposite end of the scale, and it's very suited for group extensions, and in particular for solvable groups. So the cohomological approach relies on class field theory ultimately, and on local global principles. And historically, like the first successes towards the inverse Galois problem were the result of Scholz-Reichert in 1937. They proved that all odd solvable groups are Galois, and then Shafarevich in 1956 extended it to all solvable groups. So this is suitable, as I was saying, mostly for solvable groups, but also somehow the setting, and I will come back to this later, is indicative of, like, it's more suited to deal with group extensions, maybe sometimes even when combined with other approaches. And it kind of gives a motivation to look at, instead of just the inverse Galois problem, also like local global variants of the inverse Galois problem. And this will be the Grunwald problem. Yes, there are also some other approaches that I do not want to go into more detail here. But yes, so as I was mentioning, as I was saying, the local global variant of the inverse Galois problem leads to a natural question. That is the Grunwald problem. It is as follows. So you fix your finite group G, and you ask now for an extension of Q with Galois group G, such that not only you have this Galois group G, but also you want to approximate any given collection of local extensions. So like this, you have these collections LP over QP that are Galois with respect to some subgroup DP of G. And then you want a global extension whose decomposition groups are up to conjugacy exactly with DP. So yes, this is the question. Essentially, this question was first analyzed as a theorem by Grunwald, who proved, I'm using quotes because when the proof was found out to be incorrect, but he thought to have proven that the Grunwald problem holds true for all abelian groups. Okay. So yes, as I was saying, Van Wang provided a counterexample. In particular, yes, it's very simple. If you take for your group G the cyclic group of order 8, and you try to approximate the unramified extension of degree 8 over 2, there is no such approximation with a global extension of Q. So yeah, there is no global extension of Q that is totally inert at 2 with this gamma group. So yes, there was this counterexample, and this led to a modification of the original Grunwald problem, and somehow a weak version. And it's, okay, let's say, so remember that like in the original formulation, we want to approximate at all places at all finite set of places. Here, instead, we exclude a bad set of places with S naught. And so in this variant, we ask if there exists some bad finite set of places such that we can approximate any finite collection outside of these bad places. So for instance, in the case of Z modulo 8Z, it holds true with bad places just 2, the place 2. Okay, and so Wang corrected the original claim of Grunwald, proving the famous Grunwald-Wang theorem, and that is that this statement, this question, has a positive answer for abelian G. And yes, he also gives actually a very explicit description, but it's very messy in some sense in the original formulation of what happens at the bad places. But yes, like a consequence in particular is a positive answer to this question. Okay. So what should we expect about this question? Spoiler is that we should expect it to be true, but let me give more motivation towards that. For this, I need to like introduce this auxiliary variety, SLN over G. And you can think of this as a rational, as a variety whose rational points in some sense parameterize Galois extensions with group G. Up to the action of SLNQ, they do. Like if you take the rational points of X and you quotient by the equivalence relation given by multiplication but by points in SLNQ, you obtain exactly the set of Galois extensions with group G. Not exactly, but more or less. Okay. So, yeah, this is just an abbreviation. I will say what it means precisely in a moment. So the Grunwald problem can be reformulated because of this connection that I was mentioning by saying that the variety X has the so-called weak approximation property. That means that its rational points are dense in the collections of local points, in the complete collections of local points. So note that this is a bit different from the adelic points because X is not compact, and so if you take you require no integrality condition here on this product. So it's a real product and not an ultra product. But yes, if X was proper, then this would be also the adelic points. Okay, then the weak version is equivalent to the weak approximation on the same space, where weak means that we eliminate finitely many places. And in between these, we can actually put something else that arises from the field of like study of rational points, and that is we can ask that X has weak approximation up to Brauer-Manin obstruction, so that the rational points are dense in the Brauer-Manin set. And then we can define like this Grunwald problem with Brauer-Manin obstruction as being equivalent to this thing, that X has that the quotient SLN over G has weak approximation up to Brauer-Manin obstruction. Yes, so the implications that I mentioned here are due to Cogliotelen and Ekedal. And yes, I just want to mention as like that so the Grunwald problem is stronger than Grunwald problem with Brauer-Manin condition, and this is stronger than the weak Grunwald problem. The last implication is not immediately visible, but it is essentially due to the fact that this Brauer-Manin obstruction is a finite obstruction. It comes from a finite group that obstructs only on finitely many primes. And one can actually also get a control on these primes. So the Grunwald problem with Brauer-Manin obstruction implies in particular this weak version of the Grunwald problem. Okay. Now it is a conjecture of Cogliotelen that every unirational variety should satisfy weak approximation up to Brauer-Manin obstruction. So actually even more, like you can also put rationally connected with a rational point, with a smooth rational point. So in particular, this conjecture implies a positive answer, would imply a positive answer to the Grunwald problem with Brauer-Manin obstruction. And yeah, so and even more so to the inverse Galois problem. So yes, so basically we kind of expect a positive answer to this variant of a Grunwald problem. In particular also to the weak variant that I formulated before. Okay, some results on the Grunwald problem. The first result is, I already mentioned it, is for abelian groups. This was proven by Wang and Grunwald, essentially. Wang corrected proof of Grunwald. So they don't just prove a weak version, they actually prove the more precise version with Brauer-Manin obstruction, even though they didn't use the Brauer-Manin obstruction terminology. Then, yes, the Grunwald problem, and here there is no need actually to consider the Brauer-Manin obstruction. For solvable groups with odd order, and here, yeah, remember at the beginning I said everything holds over every number field, but here actually you need K to be Q. And this was done by Neukirch in 1979. And then, yeah, with Brauer-Manin obstruction was done by, for iterated semi-direct products of abelian groups was done by Harari in 2007. And lastly, the last result I wanted to mention are supersolvable groups. This is by Harpaz and Wittenberg in 2020. And let me say what a supersolvable group is. It's a group with a filtration of normal subgroups such that each quotient is cyclic. So the most basic example is RP groups, because then you can take the center, a cyclic subgroup of the center, quotient by that, and then construct the whole thing by induction. So yes, they gave a positive answer to this Grunwald problem, to Brauer-Manin obstruction for supersolvable groups. So the theorem that I present today is a generalization of these two solvable groups. And so the theorem, yes, this theorem here essentially starts with So what I actually prove is a fibration theorem that is a more technical statement that I will present in a few minutes, but combined with a certain descent technique of Harpaz and Wittenberg, this gives also the Grunwald problem for solvable groups. So to introduce the fibration theorem that is my actual main result, I need to somehow talk about the descent method by Harpaz and Wittenberg, and how it connects the Grunwald problem to a problem about rational points on certain fibrations. Okay. So yes, let's start to, I'm just gonna give a general idea and rough overview. Okay, so let's start with a solvable, finite solvable group. Take the commutator subgroup, G prime, and take the abelianization, A, G quotiented by G prime. Then we can introduce the quotient SLN over G and the quotient SLN over G prime. And these two quotients are, one is we quotient by more stuff, so we get a cover of U by V, and this is Galois with group A, the quotient, because G prime is normal in G. Let's also give some names to the compactifications. Now you consider like an auxiliary short exact sequence. 1 A TQ1. So remember A was this finite abelian group, the abelianization of G, and we embed it in a torus T such that the quotient is quasi-trivial. So being a quasi-trivial torus means just being defined in equations as being some norm form being different from zero. Yes, so there is such a short exact sequence. And now we construct the auxiliary variety, where you take y times t, and you quotient by the diagonal action of A on both factors. So on one side, we're quotienting y, and so essentially we're getting something that is birational. So we're getting something that is birational to x. On the other side, we quotient t by a, and so we get q. So we get two projections from this diagonal quotient to the two factors, and one is over x, and the other one is over q. So let me re-give the diagram here. And now the idea, so remember that we're trying essentially to prove that all collections of local points on X that are Brauer-Manin unobstructed can be approximated with a rational point. So we want to start with a Brauer-Manin unobstructed collection of points, and we want to find a way to approximate it with a rational point somehow. So when we have such collection, the first thing we do is we lift it through this first projection pi. And this is done by the theory of open descent. So essentially results due to Harari, Skorobogatov, Tsao, Harpaz, Wittenberg. And now we get a collection of local points on Z. And this is the setting where the fibration comes into play, because the fibers of F are twists of the variety Y. And so if one can approximate this collection with a collection that lies on a fiber, then since Y is birational to SLN over G prime, we now get a collection on this quotient by something that is smaller and it proceeds by induction. So I'm a bit cheating here in the sense that there are a lot of twists and stuff, and one needs to work in a more general setting, but like I just wanted to give a rough idea of what's happening and where the fibration that I'm gonna talk about comes into play with the Grunwald problem. Okay. So yes, the main theorem that I wanna that I prove about with fibration is the following. You have an f from z to q. For instance, this could be the f that I introduced here. But in general, you could take any proper smooth morphism of k varieties, where q is a quasi-trivial torus, and for which there exists a geometric torus that acts on z and transitively on q, making f equivariant. But you could also just take the f here, like from this z to q. Then if the fibers are rationally connected, we get, there is this statement. So that here, zq omega just indicates collections of local points. And so it says that Brauer-Manin unobstructed collections of local points can be approximated by Brauer-Manin unobstructed collections of local points on the fibers. So again, using this kind of statement and then this induction with the Harpaz-Wittenberg descent method, one arrives at the Grunwald problem with Brauer-Manin conditions. Yes. Just this bullet here just indicates that the real connected components are collapsed to a point, but it's not important for what I'm going to talk about. Okay. So in part, yes, this fibration gives actually like also a bit more than the Grunwald problem. It generalizes like is a supersolvable descent of Harpaz and Wittenberg to a solvable descent. And so this can be used to give new examples to the inverse Galois problem. And so, for instance, you get like semi-direct products of A5 by solvable groups. And this generalizes this earlier example with where G was super solvable, was only super solvable. And yes, so this uses this combines these local global ideas for solvable groups with A5 is not just a random group, it's a group that I also mentioned. Okay. That's a bad idea. Okay, that I also mentioned here because the quotient AN over A5 is rational. So it lies into this setting where this approach by Noether is successful. And one can actually prove a bit more than what Maeda did, and this was done by Bugattas and Neftin, and what they prove, which is a result on homogeneous spaces, can be combined with the solvable descent to get this example. Okay, yes. So lastly, I wanted to talk about a little bit the idea of the proof. So here, let's say, first of all, the main problem, let's say the biggest obstacle is that the Brauer-Manin obstruction on the big space Z somehow does not account for all of a Brauer-Manin obstruction on the fibers. So this is somehow the last but also most difficult step of the proof. So before going into that, let me talk a little bit about the other steps, which I mean also pose difficulties. And yeah, the first thing I want to talk about is lifting local points. So here you start with a collection of local points on Z, and you want to approximate them. So the end result and would be to approximate them with something Brauer-Manin unobstructed. But for now, let's ignore the Brauer-Manin obstruction. Then the idea to obtain such an approximation is to construct a certain multisection that is like it needs to be a subcover of like this specific profinite cover of a quasi-trivial torus Q, where so T1, Tn here are a basis of characters permuted by the Galois action, and here in this spectrum you should take the roots with arbitrary denominator of all but one of the TIs. And so this gives a profinite cover. It's almost like the universal cover of the torus, but it's not really, in the sense that like you're forgetting one of the variables. Then, so the idea is to use this multisection to lift local points. And in particular, one can use ideas of Shafarevich used in his first paper from the 50s on the inverse Galois problem for solvable groups, to find a rational point on Q that approximates the images of these local points, and such that outside of the set where we're approximating, either we have an integral point on the torus, in which case it essentially follows from the Langweil estimates and Hensel's lemma that we can lift the localization, or we lift via the multisection, and then we can use the multisection to lift the point to Z. So these two combined give us a point, a Q omega point on ZQ. But so far we know nothing of a Brauer-Manin obstruction. But combining these two, we get a local point here, a collection of local points here. Okay. So yes, this is the first step. So now we need to start thinking about the Brauer-Manin obstruction. And the first thing to do is somehow to uniformize the Brauer groups of the fibers, because per se they it might not be immediately clear that there is a way to parameterize them uniformly, and that they're not just some random group associated to each fiber. But yeah, this is not so much of an issue, and one can define. I mean, the definition is kind of ugly, but because it involves derived categories and so on. But anyway, there is a certain group, a finite group, when one can define associated to the fibration. It has two important properties. So I'll start with the second, and that is that it's isomorphic to the Brauer groups of the fibers, quotiented by constants, over an Hilbertian subset. So it provides the uniformization we need. And then the first one is about where this group lies. So there are these natural exact sequences that I wrote here. So this Brauer, I don't know, called the horizontal Brauer group is possesses as a subgroup the Brauer group of Z quotiented by the pullback of Brauer Q. And then what remains goes into VH3 of QGM. So in some sense, there is an obstruction for a class in the Brauer groups of the fibers to come from a global Brauer class, and this obstruction lies in the H3 of the base. And this 3 is kind of important because it's what will come out later when we will take like the triple variation, and triple is exactly because of this 3 here. Okay, so yeah, I should say similar uniformizations already appear. Yeah, for instance, in work of Bright, Browning, Locke. So yes, this is the way to uniformize the fibers. And okay, once we do that, we now have, thanks to these sequences, we now have various species in which we can decompose this Brauer group of the fibers, and it's the image of Brauer Z. Then we also have the image of a Brauer group of a generic fiber, which is a little bigger, but very slightly. And then the rest, which goes into the H3, or the H3 eta G. And so, okay, the first two pieces, the first piece requires no new ingredients. It's just laborious technical work. Also, the second piece requires some computation of residues, but is just laborious work on the setup that is already here. And then the last part instead poses a real issue and like could actually still obstruct. It's the part that injects into VH3. Okay. And so somehow to deal with this last issue, one can use this lemma by essentially Alexander Smith from, his work is way more general than this lemma here. This is a simple lemma that can be proven in 2 lines, and we'll present the proof. But somehow it's as if it's like a baby toy of some of his ideas. So okay, the lemma is as follows. Take a finite abelian group. It's a combinatorial lemma, purely independent of everything that I said before. Take a finite abelian group, and then there exists a function, like for every sufficiently large integer m, there exists a function from a 4-dimensional grid to A, such that for any primitive according to this functional, delta 3, this primitive has a 0. Delta 3 is just the compositum of the 3 discrete differential operators. So it's like an algebraic sum of 8 terms with plus or minus ones. And yes, so essentially, yeah, this is the lemma that constitutes the main new ingredient. And the idea, like philosophically, the way to think about it is that if you have some function f that you don't know how to control, which is our case, it's the Brauer-Manin obstruction on the fibers. It's the last piece of a Brauer-Manin obstruction. And you don't know how to control it, but you can control the triple variation, or actually any Kf variation would also work. And you can set it equal to some prescribed function. Then you can manage for this f, which is the Brauer-Manin obstruction in our case, to trivialize at some point on the grid. So yes, so we want to apply it with this idea. But before going into the application, let me say because I think that the proof is very fast, so you can present it here. You just take the restriction of this delta free operator from the functions that do not have a zero to all the functions on one variable less. And then this is not surjective simply by computing the cardinality of left-hand side and right-hand side. The left-hand side is like this thing, cardinality of a minus 1 to m cubed. The right-hand side is cardinality of a to m minus 1 cubed. But yes, this left-hand side, as m goes to infinity, is much smaller than the right-hand side. Because the coefficient, like if you write it as e to the log something, then the coefficient multiplying m cube on the exponent is smaller on the left-hand side. So now by taking a g in the complement of the image, you get a function, all of whose primitives attain a zero. Okay, yes. So this was this lemma. Now, yes, what remains to do is to deal with the last piece of the Brauer-Manin obstruction. So we apply this lemma to the group A, that is what remained of the Brauer group. So it's the co-kernel of this map, and we take the dual just for technical reasons. Okay, and then the technical theorem that allows to conclude the proof of the fibration theorem is that for every function g from some grid to A, there exists a grid of parameters m like this inside the torus, such that for every point on the grid there is a point lying above it, a collection of local points that is Brauer-Manin obstructed with respect to what we already dealt with, so Brauer Z eta, that approximates what we want to approximate, and such that the triple variation of the rest of the Brauer-Manin obstruction is given by G. Yes. So in particular, this Brauer-Manin obstruction on the fibers is like a primitive with respect to this delta free of G, and so attains a zero. And this means that we find a parameter with no Brauer-Manin obstruction at all on the fiber, and then also a collection of so with no Brauer-Manin obstruction near the points that we care about, and so we can approximate as wished. And yes, I think that's all actually. Like this concludes the proof of the main fibration theorem, and yeah. So thank you for the attention.